Okay. This talk is given by Elfar Adalsteinsson. That's me. I'm presenting the research that I run in my group and with colleagues at MGH in Boston. And a big area of interest to us over the last 5 years, 5, 6, 7 years, has been addressing problems that show up in ultra-high field human MRI. So 7 Tesla, okay, is a high field strength in MRI, and people go to high field strength to get higher signal, right? That's great, that comes from physics. There's also a penalty that's induced by the physics. So this signal, ideally, would be uniform everywhere in the brain, but this is bright in the middle and dark at the center, right? And there's a wavelength effect that becomes more severe with a higher field strength. So you bought a scanner for €1 million per Tesla, and you move 5 centimeters off the sweet spot, and you're paying a heavy price in precisely the parameter that we're going after this in our signal to noise. So we're addressing this with a technology called parallel transmission. By now, the method of mitigating the inhomogeneity of this RF field is actually quite well understood, and this parallel transmission is a good method to solve it. So if you just briefly look at this map here, ideally what you want is all red everywhere, same flip angle everywhere, same high signal everywhere. Up here you get a lot of spatial variation in this intensity, and that's very undesirable. You lost your signal, sometimes you lose contrast, both are bad. So this method works quite well, right? What's interesting, it ties into Team MS. This solution, which is beautiful in giving you this high signal everywhere, actually compounds this SAR problem, the heating problem, the penalty that comes along with driving the RF. So, and that's a hard problem. There's a lot of groups working on it. Team MS is making very nice progress on it. And another example of a project, so this was kind of under the hood engineering. There's also work going on in the group that is more kind of physiological. So you can use properties of the MR signal to estimate CMRO2, cerebral metabolic rate of oxygen consumption. And Audrey Fenn in the group has methods named PROM. This is a very promising method to estimate the physiological parameter. And here's another contender, slightly different, but gives you maps where the intensity is not bright in gray and dark in white matter, but quantitative numbers of oxygen consumption in the tissue. We work on sort of heavy encoding problems. We live in Boston. Here's MIT. Here's the Charlestown Martino Center. The combination between these two, as I think a lot of the fellows have seen, and now expanding into Madrid, is a pretty powerful sandbox to play in. Please contact me, Elfar, at MIT EDU for any questions. Thank you.